Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, working as a professor in University of Delhi. Today, we are going to discuss about the module Atomic Force Microscope or Microscopy as we call it. And in this module, we'll deal with the introduction of this particular technique, which comes under the paper of Surface Analytical Techniques Part 1. When you study this module, and after completing this, you should be able to understand the introduction to scanning probe microscopy, information about the inventors, that is Gerd Binning and Heinrich Rohrer. We'll continue with this. Why SPM? Branching the scanning probe microscopy. It will be of, it's a branch of this, but then techniques like AFM, STM, MFM, etc. all will come under this category. Then what is the historical background of atomic force microscopy? And lastly, the advances which are there in AFM technique. Now, when we introduce this, we realize that scanning probe microscopy is a branch of microscopy that forms images of surfaces using a physical probe that scans the spectrum. It is one of the powerful modern research techniques that allows to investigate the morphology and the local properties of the solid body surface with high spatial resolution. First scanning probe microscope was invented in 1981 by Binning and the Rohrer.
AFM is very different from optical microscopy. There are no lenses. There is no requirement for a light source to illuminate the sample. There is no eyepiece to look through. The microscope itself does not even look like a typical optical microscope. The imaging technique consists of a mechanical device which is able to measure very small force when atoms or molecules come close together. So it was named atomic force microscopy. Cantilever are at the heart of an atomic force microscope. A critical part of the device called the cantilever is a plate spring which is fixed at one end. At the other end, it sports a pointed tip. The tip can be moved across sample surface line by line, just like a lawn mower in the garden. The pointed tip is brought into the contact with the sample and move across the surface. The instrument measures the deflection of the cantilever as it scans, and from this information about the tip movement, a three-dimensional image of the sample is built up. How does the AFM work? AFM provides a 3D profile of the surface on the nanoscale by measuring force between the sharp probe. The probe is supported on a flexible cantilever. The AFM tip gently touches the surface and records the small force between probe and the surface. AFM is the heart of an SPM is a probe that is scanned over the sample surface to build up sum from the image. The type of image you get depend on the interaction that is measured by the probe. Image can be produced that reflect many different properties of the sample. The sample height information topography usually forms one aspect of the image, but images can also be collected that show other properties including mechanical, electrostatic, optical and magnetic information about the sample surface. Different probes and measurement systems are often used for different properties, but one requirement is that the interaction between the probe and sample is localized in some way. There is so that the measured signal is dominated by some small region of the sample closest to the tip, so that an image of a sample can be formed as the tip is scanned over the surface. This implies that the interaction must have a strong distance dependence so that only the nearest parts of the sample contribute to the interaction felt by the tip. The range of the interaction will be one factor in the final resolution of the instrument. When the interaction has a very strong distance dependence, such as electron tunneling current used in STM, the resolution can be good enough to see individual atoms, since the measured signal should be dominated by the small region of the probe and sample that are closest together. Actual probe does not need to be isolated point. The probe can be part of some structure that is more convenient to mount and scan. The size of probe can be relatively large, perhaps hundreds of microns or more, but if the interaction has a short enough range, then the signal will be dominated by the very tip region of the probe, so that resolution can be still achieved in the range from atom distance to micron. The ideas of a probe measuring a local interaction and building up an image is relatively straightforward, but the actual implementation of a system with a resolution in the range is technically challenging. Many factors come together in the development of scanning probe microscopy, including the development of piezoelectric materials that made it possible to reproducibly position and scan components with a sub-nanometer precision. What type of force are measured? The dominant interaction at short probe sample distance in the AFM are van der Waal interactions. However, long range interaction means capillary, electrostatic, magnetic are significant further away from the surface. These are important in other SPM method to analysis. During contact with the sample, the probe predominantly experience repulsive van der Waal forces contact mode. This leads to the tip deflection described previously. As the tip moves further away from surface, attractive van der Waal forces and dominant in non-contact mode.
The inventor, Gerd Beining, born on 20th July 1947, is a German physicist who won the Nobel Prize in Physics in 1986 for the invention of scanning tunneling microscope. Beining studied physics at the J.W. Goethe University in Frankfurt, gaining a bachelor's degree in 1973 and remaining there to do a PhD with a Werner Martinson's group, supervised by Eckhard Hoening. In 1978, he accepted an offer from IBM to join their Zurich research group, where he worked with Heinrich Reurer, Christopher Gerber, and Edmund Weibel. They developed this scanning tunneling microscope, briefly written as STM, an instrument for imaging surfaces at the atomic level. This was a great discovery. The Nobel Committee described the effect of this one, and very rightly, that the invention of the STM had on science, saying that the entirely new fields are opening up for the study of structure of matter. The physical principles on which the STM was based were already known before the IBM team developed this STM. But Beining and his colleagues were the first to solve the significant experimental challenges involved in putting this into effect. This was a great discovery in the sense that one could go to the extent of atomic level on these surfaces, which otherwise was not possible. The IBM Zurich team were soon recognized with a number of prizes, which included the German Physics Prize, the Otto Klung Prize, the Hewlett-Packard Prize, and the King Faisal Prize. In 1986, Beining and Royer shared half of the Nobel Prize in physics. The other half of the prize was awarded to Ernest Ruska. In 1987, Beining was appointed IBM Fellow, and in the same year he started the IBM Physics Group in Munich, working on creativity and atomic force microscopy. Heinrich Rohrer, who was a co-worker or a fellow worker with Beining. He was born on June 6, 1933, and he died on 16 May 2013. He was a Swiss physicist who shared half of the 1986 Nobel Prize in Physics with Gerard Beining for the design of the scanning tunneling microscope. The other half of the prize was awarded to Ernest Ruska. Now, this was a great achievement on the part of Beining and Royer because they work a great deal in designing and putting STM into use. In 1963, he joined the IBM Research Laboratory in Rasculon under the direction of Ambrose Spicer. The first couple of years at IBM, he studied Kondo systems with magneturo assistance in pulse magnetic fields. Then he began studying magnetic phase diagrams, which eventually brought him into the field of critical phenomenon, which up till that stage was relatively not known. So the question which arises is, why study SPM? The SPM technique images the surface structure with atomic height resolution without the necessity of damaging the sample. The results are shown as a kind of three-dimensional image. SPM operates without vacuum, and in contradiction to electron and optical microscope, it cannot measure different other physical properties. The scanning probe microscope that can scan samples from very low scale to about millimeter scale. Here in this slide, some scales have been shown which can be put to use, or which can be scanned, which can be seen with the help of scanning tunneling microscope. The first is up to 10 to the power minus 3 millimeters. It's visible. We don't need any support. But when we go to 10 to the power minus 6 micrometer, we require an optical microscope. And 10 to the power minus 9 millimeters when we go, we need scanning electron microscope or transmission electron microscope. And below this, we require scanning probe microscope. This is a force which does the electron tunneling, etc. A diagram of first atomic force microscope. It is very clearly shown here that this is not a very big sized equipment, but is a very useful one. Now we will discuss about the history of atomic force microscopy. In 1986, by Binning et al., it was developed in the first stage, and then developed the first atomic force microscope also. Since then, the AFM has undergone continuous development in all areas. The first AFM operated in contact mode was also started around about the same time. In contact mode, the tip is mounted onto the end of a flexible cantilever and raster scans the surfaces of the sample. The tip surface interaction deflects the cantilever, which gives information about the surface topography. Samples can be analyzed in air, liquid, or vacuum. Resolution in liquid and vacuum is increased because of the absence of strong capillary forces due to a thin liquid film on all samples in air. Unfortunately, biological samples cannot be challenging to study in contrast mode or in contact mode because they are generally soft, weakly bound to the surface, and damaged easily. Efforts to image biological samples drove the development of non-contact mode in 1987. In non-contact mode, the cantilever oscillates close to its resonant frequency at a small distance 1 to 10 nanometers above the surface, and long-range attractive forces induce changes in the amplitude, frequency, and phase of the cantilever. While the cantilever itself maintains a constant separation with while scanning, the significantly lower forces by non-contact mode than by contact mode allows for ever the non-contact mode. We find that it significantly lower the forces than by contact mode, and it allows for even the softest sample to be imaged without damaging. The biggest part here is that even the softest sample can be imaged without damaging it. The fourth generation prototype was developed in 1989, and this particular one sparked interest in the commercialization of AFM so that it is used by every researcher in the area of electrochemistry in particular. The earliest microfabricated tips were developed in 1991 by Prater et al., obviously in 1991. In 1993, tapping mode was first introduced. In this mode, the cantilever oscillates at its resonant frequency, but unlike non-contact mode, the cantilever gently taps the surface during scanning, reducing damaging lateral forces. Fluid tapping, a major development for biological samples, occurred in 1994 in Hensma's lab. In this first trial, the sample, which sat on a piezoelectric scanner, was oscillated up and down and tapped the tip on oscillation cycle. The amplitude of the piezoelectric was set manually at the beginning of the image, and the tapping force was held constant by a feedback loop. Modern implementations oscillate the tip and not the sample for finer and easier force control. Smaller cantilevers were developed in 1996, allowing higher resolution and smaller scanning time by significantly reducing the moving mass and increasing the detection bandwidth. The Hansen Group began developing a new generation of AFMs that would utilize these smaller, lighter cantilevers. For biological samples, these tips were as significant an improvement as anything else can be. By reducing the mass of the cantilever, high resonance frequencies could be reached for fast imaging while maintaining a low spring constant lever that does not damage the sample. Further developments led to cantilevers on the order of 9 to 40 microns in length with resonant frequencies an order of magnitude higher than commercially available cantilevers. This was a significant development. The prototype of the small cantilever, which is there in AFM, The next prototype was a smaller cantilever AFM, as has been shown in this figure. The prototype used custom designed optics for the optical detection of the cantilever to minimize the spot size on the cantilever. This significantly reduced spot size allows for even smaller cantilevers to be used, resulting in higher speeds and lower forces. Technical capabilities. AFM images show critical information about surface features with unprecedented clarity. The AFM can examine any rapid surface, any rigid surface, either in air or with the specimen immersed in a liquid also. Minor and major differences between smooth surfaces are shown dramatically in a very clear manner with the help of this. On one hand, the AFM can resolve very tiny features, even single atom that is present can previously be seen. On the other hand, the AFM can examine a field of view larger than 125 microns, that is 0.005 inches. This is done so that we can make comparisons with the other information, as example, features seen in the light microscope or hazes seen by eye. The AFM can also examine rough surfaces since its vertical range is more than 5 microns. Our analytical reports of AFM results include three-dimensional images and quantitative data analysis such as feature sizes, surface roughness, and areas. The cross-section plots integrated and interrupted in the context of your problem. Large samples fit directly in the microscope without cutting. We can examine any area or flat specimen up to 8 inches, 20 centimeters in diameter and up to 0.5 inches, 12.5, 12.7 rather, thick. So we have designed custom adapters to accommodate SEM stubs, microtone blocks, metallurgical mounts, and other old shape and sizes up to 1.5 thick. We can quickly find that documents and the measurements, the location of interest using the built-in optical microscope with magnification up to about 2000x, that means 2000 times, can be done. For comparative studies using different probes and scanning modes, we can find this spot within 1 micron. How the AFM makes a 3D images. In contact mode, a tiny stylus gently contacts the specimen. As the XYZ translator scans either the specimen or the stylus horizontally on a raster pattern XY, the stylus rides up and down the surface hills and valleys. The diffraction of the stylus is registered by the laser or photoiodide sensor, and the XYZ translator adjusts stylus and specimen depending on the microscope up to or down Z to restore the stylus to its original orientation. The computer stores the vertical position at each point and assembles the image. For image display, we select the vertical and horizontal ranges instead of or independently. It is done to the best present in the surface structure. For image display, we select the vertical Z and horizontal XY ranges independently to best present the surface structure. This has been repeated because of the importance of this particular point. Using dual magnification, the AFM combines the wide field view of a scanning electron microscope SEM with vertical resolution which exceeds that of transmission electron microscope, that is called TEM, and is very widely used in the area of corrosion research. The ratio of the vertical to horizontal magnification can be very large, 1000 or more, to allow easy acceptance of different or differences between the very smooth surfaces. The AFM is being applied to studies of phenomena such as abrasion, adhesion, cleaning, corrosion, etching, friction, lubrication, plating, and polishing. The real-world examples presented on our web page indicate the breadth of AM applications for problem solving. Yet, they represent only a fraction of our experience at advanced surface microscopy. AFM images show critical information about surface features with unprecedented clarity. So, students, after giving you the introductory part of AFM, now let us summarize what we have learned in this module. The atomic force microscope is being used to solve processing and materials problems in a wide range of techniques affecting the electronic, telecommunications, biomedical, chemical, automotive, aerospace, and the energy industries. The material under investigation includes thin and thick film coating, ceramics, composites, glasses, synthetic and biological membranes, metals, polymers, and semiconductors. The AFM can examine any rigid surface, either in air or with the specimen immersed in a liquid. Minor and major differences between smooth surfaces and the rough surfaces are shown dramatically. On one hand, the AFM can resolve very tiny features, even single atom, that were previously unseen. On the other hand, the AFM can examine a field of view larger than 125 microns, that is 0.005 inch, so that you can make a comparison of the other informations. The AFM can examine rough surfaces since its vertical range is more than 5 microns. Analytical reports of AFM or AFM results include three-dimensional images and quantitative data analysis. Such feature sizes, surface roughness, and area and cross-section plots integrated and imprints can be interpreted in the context of your problems. Compared with scanning electron microscope SEM, the AFM provides extraordinarily topographic contrast, direct height measurements, and unobscured view of the features or view of the surface features. No coating is necessary while using this. Compared with transmission electron microscope, three-dimensional AFM images are obtained without expensive sample preparations and yield far more complete information than the two-dimensional profiles available with cross-sectional samples. Compared with optical interferometrics, as we have seen in the area of magnetic studies, microscopes, optical profilers, the AFM providers, and the unambiguous measurement of the step heights independent of reflective differences. ये लास्ट लाइन दोबारा compared with the मैं दोबारा बोल रहा हूँ compared with the optical interferometric microscopes, that is optical profiler, the AFM provides unambiguous measurement of step heights independent of refractivity differences between the materials. I am sure you would have appreciated AFM's introductory part. Thank you very much.